Okay, so I want to talk about a survey of very distant RLI stars that we've gotten spectroscopy of. This project was really instigated, I think, by Judy Cohen. It's why I listed her first. And there have been a few people at Caltech who've worked with her on it. Nina Hrnicek was a postdoc of hers, and Trinity Bento was a summer undergraduate student. This really got started after Branimir Cesar was a postdoc at Caltech as well. And it grew out of the pan-star sample of RLI stars. And then Ian Thompson and I got involved in it, and Chris Burns here helped us out a lot, and Chris Sneeden as well. So now, how do I make the next? This goes forward? No. The right, that's what I did. Yeah, okay, good. Okay, so the samples came from this pan-stars survey for RLI stars, which is Cesar et al. 2015. And there are, in our sample, the one that we tried to get spectroscopy of as many as we could, there were 3,300 potential targets. They excluded the galactic plane up to plus or minus 15 degrees. And they also excluded the Sagittarius plane because we didn't want to just take a lot of spectra of stars in Sagittarius. We thought other people were doing that. And the limitation was that we didn't do any stars that were less than 30 kiloparsecs from the galactic center. And then from these, the potential targets, we actually sort of statistically chose in funny ways several different samples. There's a general one, which was just pick a star, any star. Then there were ones with close pairs we thought might be associated with each other. There were ones that were associated with distant dynamical features of the Sagittarius dwarf. And anyhow, with all of these samples, we got a total of about 600 unique objects with spectra. A few have repeats. The general sample is the one I want to talk about in this talk. There are 400 objects in the sample. 300 were observed with Magellan and Mike at very high resolution, 15,000. And 112 were observed with Keck and ESI at about half that resolution. And the typical magnitudes of these stars are like 18th and 19th. They sort of go from 17.5 to 20.5. So the top shows the sample of pan-stars RLI just in RA and DEC. And there are zones of, this is where the galactic plane is. This is where the Sagittarius plane is. So unfortunately, we sort of cut out a lot of the sky, but it's what it is. And so there are several areas in this. The ones that we actually ended up getting are shown in the lower panel. And what you can see is we were more efficient at observing in the southern hemisphere than in the northern hemisphere. It just came out that way. There's an interesting thing in this diagram, which shows up better, I think, in the next diagram. So this is just the same thing, but in galactic coordinates. And what's curious is there are a lot of stars here compared to here. And so like, what's up with that? And I don't know. I've been trying to figure it out. It's possible it has something to do with the pan-star selection, but I think actually that's pretty good everywhere else. Or else it's, there have been a number of papers that have mostly appeared since we started this project about sort of the wake and the dynamical effects of the Large Magellanic Cloud, and maybe it has something to do with that, but anyhow, it's curious. Okay, so then just expanding upon this funny region, what you can do is make the same diagram, but divide it up into 3 shells in galactocentric radius, which have the same number of stars in each cell. I thought that would make it perceptually easier. But then I translated it to what it would look like, not from the sun, but from the center of the galaxy, because it's galactocentric radius. That made sense. And so actually, I think in the middle shell, maybe this thing is more the contrasty and most conspicuous, a little less so than it looks in there. Anyway, but it's sort of everywhere anyway, so that's what it looks like. Okay, so we got spectroscopy, and the idea was to observe at a phase of about 0.35, where the velocity that you observe is close to the rest velocity, the systemic velocity of the RLI, the average velocity. And the phases, we had a fantastic tool that was written by Chris Burns that enabled us, while we were picking targets during the night, to choose the stars that were at the right phase out of 3,000 stars. And then after the fact, we got improved phases from ZTF for most of the stars that we observed. So we actually have quite good phases for the times of observations of the spectroscopy. Now, on the other hand, the signal and noise of the spectra is terrible because we are interested in quantity, not quality. The velocities were derived by cross-correlation of the metallic lines, not the Balmer lines, with a composite stellar template that Ian had ready to go, roughly from 4,000 to 5,000 angstroms. For the ESI data, it went to 5,400. And the metallicities is obvious when we were deriving the velocities that some had strong correlation peaks and some had weak correlation peaks. So the metallicities basically comes from the strength of the cross-correlation peak. But we actually had a project with the summer undergraduate student at Caltech to derive a method to do this in a sort of careful way. And so what we did was Chris Sneeden provided us with a grid of high resolution synthetic spectra covering all the phases and metallicities. And then the synthetic spectra are really high, much higher resolution than ours. They have to be smooth to match the width of the observed stellar spectrum. And then you subtract 1 from the continuum so that the sort of the baseline value is 0, you know. And then you calculate the autocorrelation of the synthetic spectrum and the cross correlation of the synthetic spectrum and the object spectrum. And when you have the right synthetic spectrum, they should look the same. So then we have an iterative search for the smoothing width and metallicity for which the width and height of the peak of the correlation function of the two correlation functions match. And we call that the place where the correlation ratio equals 1. So we call this the correlation ratio method. And you could ask, well, why didn't we just do direct chi-squared fitting, which is what is all the rage nowadays? And the fact is that this method statistically has a very well-defined and sharp statistical minimum. It's just the place where this ratio crosses 1, and it's a really strong power, you know, of the function of the metallicity of the synthetic spectrum. Whereas if you do direct chi-squared fitting, these are terrible spectra with a lot of noise. And the chi-squared minimum is very broad and shallow. And I think that there are systematic effects that can sort of tip the baseline of that broad, shallow minimum and make a big error in the metallicity that you derive. Anyhow, I sort of am confident in this. I think if it's done right, it's actually not that different from chi-squared fitting. Okay, so this shows what one of our spectra look like. This is better than average signal and noise. There are ones where the noise has 3 times the amplitude of this, which is terrible. So the blue is the spectrum, the orange is the synthetic spectrum, and the green is the residual. And then there are some diagnostic things about how well the residuals stay at 0 and what the RMS is as a function of wavelength. We cut out the regions around the Balmer lines, et cetera. And then
what's the difference between green and blue in this thing?
So the orange line is the synthetic spectrum. So like here are absorption lines, right? The blue is the object spectrum. So that's
the green.
The green is the difference. It's the residual between the object spectrum. Okay. Okay, so then you get the correlation functions, and you can see they really match when you have the right one. You can estimate the error, whoops. You can estimate the error from the sort of baseline noise of the correlation function. Okay, so then we have metallicities, we have positions. You can plot the metal abundance versus the radius from the galactic center, and this is what you get. You can see there are very few metallicities that are more metal rich than about -1.4. There are some which we know at least some of these are good that are more metal poor than -3. If you just say, what's the metallicity distribution function look like? This is the cumulative distribution. Between 30 and 40 kiloparsecs, the median is about -1.8. Between 40 and 50 and between 50 and 70, it goes up closer to 2. I think maybe this difference is real. If you go back to the previous thing, you can sort of see, well, maybe there's a sort of a clump in here which skews it a little. You can do the same thing. What's the radial velocity versus the distance from the galactic center? And you can see here the velocity dispersion is not as high as what Andy Layden was talking about. This is way out in the halo. If you take a cumulative radial velocity distribution, what you find is that the velocity of dispersion tends to be about 110 kilometers per second. Maybe in the furthest sample, it's about 100, a little less. I'm not sure how statistically significant these are. And there's a tendency for the closer ones to be a little off from 0. And is that believable or not? I'm not sure. It's just, I don't think it's as significant as the metallicity difference. What's curious is if you plot the radial velocity versus the longitude instead of the distance from the center, in this region, it sort of looks smooth. In this region, maybe it's kind of clumpy. So there are things in here, I think, to sort of follow up on and see if there's things that are real there. Then I downloaded all the Gaia proper motions for these. And you can say, OK, what is the error in the proper motion, the velocities, the tangential velocity that you derive, depending on the distance from the sun. And of course, it gets terrible because the stars are faint, the errors go up, and then they're further away. So then the velocity error is even bigger. So, but if you just pick the closest ones, it's still kind of terrible. But I really wanted to be able to derive this diagram, which Anna knows very well, which shows sort of the angular momentum around the z-axis of the galaxy and the total energy of the orbit. And the interesting, this should be 2020. In 2000, I do was probably in kindergarten. This is from the H3 survey of giant stars. There are 11 stars that are about 6,000 that are more distant than 30 kiloparsecs in the H3 survey, whereas there are no stars less than anyway. So this is sort of the disk of the galaxy, or maybe the thick disk. This is Sagittarius. This is the Gaia sausage. This is what ours look like. And first of all, given the errors in the tangential velocities, I'm amazed that it's not much wider. The other thing is you can see there are no negative energies. And I think that's just because they're way out in the potential of the galaxy. If they were in close, they'd have a big negative energy because of the potential. So this diagram sort of, I don't think it's actually revealing much, but I wanted to see it. But it does show that, it's more consistent than I thought. And the velocities from the Gaia proper motions in data release 4, this is already based on data release 3, early data release 3. So they'll get a factor of 3 better. And in data release 5, they'll be like 6 or 8 times better. So it'll get better. And then I just wanted to quickly return to, like, what is this thing? And the blob, and I was doing this like last night, but the selection is basically everything below the plane of the galaxy between longitude of 0 and 90. And the metallicity inside the blob is minus 1.8, and outside the blob, it's minus 2. And it's based on hundreds of stars, and the dispersion in the metallicity is really like 3/10. So I think this might be significant. But if it's not, if it really has a metallicity effect, it's not just a dynamical wake because it's a population. And then the rate of velocity, which could be a dynamical effect, that's actually not so different. So this shows the metallicity distribution outside the blob and inside, and there's not so much of a tail, although there's a pretty high point here, and there's sort of a shoulder here. I think they're different. And then I plotted radial velocity versus metallicity for the ones inside and outside. And anyhow, it's new, and I don't quite know what to make of it, but it's just an interesting set of questions. Thank you.
Thank you. Okay, maybe one quick question, and then we'll go get one of y'all.
You want to, could you plot your blob on the LZ versus C total diagram?
Yeah, in principle, but yeah, I mean, yeah, basically I spent a lot of the last 2 months just getting the table of observations all whipped into shape. And then I had 4 days to plot X against Y, and that's what you saw.
Okay, well, let's thank Shek and all the speakers.